we'd like to introduce our new work, two-stream networks for weakly supervised temporal action localization with semantic-aware mechanisms. A novel two-stream network that combines the merits of MLL and attention mechanism is proposed to resolve weakly supervised video action localization. To perceive semantic information, a learnable dictionary with Euclidean constraint is designed to facilitate similar representations to be considered as the same action class. Extensive experiments on tumors and ActivityNet benchmarks demonstrate that our model caused remarkable advances. Besides, substantial ablation study also reveals that the proposed two-stream structure and semantic-aware models are of effectiveness. Specifically, given an untrimmed video, the model is expected to predict the start and end position of the action in the video. There are only video-level category labels available during training, and no frame-level annotation information. For video localization tasks, the labeling cost is actually higher. Current SODA solutions mainly rely on ML-based or attention-based technologies. However, ML-based method excessively focuses on the global features and loses local details, while the attention-based method uses all the detailed features and easy to fall into a suboptimal feature combination without supervisory signal. Another point to mention is that both methods fail to consider the semantic information between video frames. The principle of ML-based method is as follows. For each frame of the video, the category confidence of the frame is independently generated. In order to obtain confidence that the video belongs to a certain category, take the average of the top K confidences of all the frames in the video in the dimension of the category. The selection of K is the key, generally proportional to the length of the video. Here is a case where a small number of frames with high confidence may be selected and mislead the optimization process. In fact, the entire localization task has not been completed, but the loss is already very small, and there is almost no gradient signal for update. The fundamental reason is that the classification task is different from the modeling of localization. This method can only obtain frames with salient features because they are not conducive to classification. As analyzed above, the algorithm is also very sensitive to the selection of the hyperparameter K. As for attention-based method, let's take an example. There are 3 scores generated for each frame of the video, representing the probability confidence that a current frame belongs to the action instance, background, and context respectively. Then the features of these frames are combined through the confidence level by means of convex combination for the final video classification. The problem is that there may be multiple feasible combinations, and the model is likely to be stuck in suboptimal solution. When classifying the foreground, context, and background, regarding the ground truth setting, add a new background category dimension. In this way, the context category is related to both the background category and the action category, using supervised signals to distinguish contextual features from action instance features. Although weakly supervised, there is no explicit supervisory signal at the frame level, but we believe that frames belonging to the same category should have similar features. This mechanism needs to be guaranteed by explicit modeling rather than letting model learn implicitly, which will cause great difficulty in model learning. An example of writing is given above. The same clause represents similar features, and the depth of color represents the degree of similarity. We hope that the model can learn this ability. It is inconvenient and inappropriate to directly cluster the features of all frames, so an intermediary is introduced. A dictionary structure is introduced to store the feature prototypes corresponding to each category, and the output frame features of the same category and the prototype features of this category are aggregated. The size of the dictionary is equal to the number of categories in the dataset. L2 normalization features are applied. Euclidean distance is used to measure feature similarity. The model uses two branches. The ML branch extracts global information, and the attention branch extracts local information. The results of the two branches are averaged and pulled as the final output of the model through post-fusion. A dictionary structure is introduced to store the feature prototypes corresponding to each category, and the output frame features of the same category and the prototype features of this category are aggregated. We verify the proposed model in tumors and ActivityNet datasets and achieved amazing results. Our ablation study shows that with all lost items, the effect is optimal, and the introduction of each lost item brings positive performance improvement. The performance of some variants is better than that of some current mainstream methods. We believe that the advantages brought by the model results in this phenomenon. Use the classification loss term as a baseline to explore the impact of the structure of the two branches on performance. The result does prove that the advanced performance of the structure, but it is more serious to use only the attention branch. We also gave a visualization case with various loss terms. So here is my presentation. Thanks for listening.